In the last lesson, we explored how electrons are arranged in atoms. Now we will learn how scientists confirm this arrangement with real experimental evidence using photoelectronic spectroscopy or PES. What is PES? PES is a technique used to measure how tightly electrons are held in an atom. It works by firing high energy light, usually UV or X-rays, at atoms. The light knocks electrons out of the atom, but only if it has enough energy. Each photon of light carries a specific amount of energy calculated by E equal hv, where E is the photon's energy in joules, h equals 6.626 times 10 to the power of negative 34 joules per second, also known as Planck's constant. V is the frequency of the photon in hertz. If you're given the wavelength instead, use C equal lambda V, where C equal 3 times 10 to the power of 8 ms, speed of light. Lambda is the wavelength in meters. To remove an electron, the photon must have more energy than the electron's binding energy. If it does, the electron is ejected. If it doesn't, nothing happens. Example, a photon has a wavelength of 1.5 times 10 to the power of negative 7 meters. The binding energy of the target electron is 1.2 times 10 to the power of negative 18 joules. Can this photon remove the electron? Step 1. Use C equal lambda V to calculate the frequency. So V equals 3 times 10 to the power of 8 divided by 1.5 times 10 to the power of negative 7 gives us a value of 2 times 10 to the power of 15 Hz. Step 2. Plug this value of frequency V into E equal hv. So E equals 6.626 times 10 to the power of negative 34 times 2 times 10 to the power of 15 gives us 1.3 times 10 to the power of negative 18 joules. Step 3. Compare to binding energy. Photon energy 1.33 times 10 to the power of negative 18 joules. Binding energy 1.2 times 10 to the power of negative 18 joules. Since the photon has more energy, it can remove the electron. What PES graphs show? PES data is shown as a graph. X-axis binding energy, how strongly each electron was held. Y-axis relative number of electrons, peak height. Each peak tells us where electrons are, which sublevel, how tightly they are held, and how many electrons are in each level. Example, PES of lithium, 1s2, 2s1. In the PES graph of lithium, you would see a taller peak at higher binding energy, 1s2, electrons closer to the nucleus, a shorter peak at lower energy, 2s1, electron. This matches the configuration, 1s2, 2s1. PES gives us direct experimental confirmation of this electronic structure. Summary: PES uses high energy photons to remove the electrons from atoms. The energy of the photon must be greater than the binding energy to eject an electron. By measuring the energies and the quantities of ejected electrons, PES reveals how electrons are arranged in atoms. PES graphs show peak height, number of electrons, and position, how tightly they are held, helping confirm electron configurations. If you found this helpful, this was just a small part of a full in-depth chemistry course I created. In the full course, you will find structured lessons, downloadable resources, practice problems, and quizzes to really master the material. Check the link in the description to start learning the full course today. I would love to see you inside.